Looks like everybody's filtered in here. So hi, good morning, everyone. My name is Joelle Miles. I'm the Program Director of the Master Advanced Study in Engineering program, also known as the MAS-E. And I'm really excited to be here today for this discussion about how our innovative new master's degree program here at UC Berkeley can help engineers and other STEM professionals accelerate their careers. In addition to our faculty panelists today, whom I'll introduce in just a moment, we're also joined here by my colleagues Emma Hobson and Tung Nguyen, who you may see replying to your Q&A in the Zoom functions. So we're going to jump right into it. Here on our faculty panel today, we have Tarek Zodi, Professor of Mechanical Engineering. He's also our Faculty Director of the MAS-E program. We have Mark Mueller, Associate Professor of Mechanical Engineering, Scott Mora, Associate Professor of Civil and Environmental Engineering, and last but not least, Jun-Chao Wu, Professor of Materials Science and Engineering. So we're going to jump right into the questions here. The MAS-E program is brand new at UC Berkeley here. It is a professional master's degree. I'm sure you all have read about it in order to sign up for this webinar. It's really a unique program for Berkeley and in the online learning landscape in general. So I'd like to ask Tarek, since you were so involved in the program from the very beginning, what gaps or opportunities did UC Berkeley see in the engineering and education landscape that motivated you to create this unique degree?
Yeah, so online degrees obviously are not new, but what we did is we really took a sort of a survey of all the online programs that were out worldwide, because many schools had tried to make attempts at this and tried to see where there were problems and where they could be optimized into trying to construct a brand new degree that had all of the things that we wanted, which were very technical, high-end, cutting-edge industrial type courses, and at the same time would make it doable for a working professional. So part of the landscape and what motivated this was to make it as easy as possible for people that are working in full-time jobs, have children, have complicated commutes, things of that sort, and to tamp down on the effort of having to get to the class and take a 3-unit full online class, if it's even online. We wanted to fix those kinds of things. So one of the things we did is we said, well, the granularity should be 1-unit classes, because those things are things that people can actually do between 5 and 8 weeks a piece. They can fit it in between their individual schedules. We mixed also asynchronous with live. So there are asynchronous work study programs, and then there are live help sessions with the faculty. So there was a healthy mix of that as well. So people from different time zones would have the ability to work on these kinds of projects. And we, of course, tapped our ladder rank faculty, which is a key thing. It's the actual faculty that teach these classes at UC Berkeley. They're not lecturers or people that are substitutes. They're the same people that teach the classes in person as they do online. So all of these things were important for us to create what we believe is a very technical and cutting edge living degree that reflects what's going on in industry and society. So this started in earnest shortly before the pandemic. And what happened was the pandemic also forced all of us worldwide to become much more dexterous with online activities. So we fast forward 5 years later, and now we're at a point where it's an everyday experience to have a Zoom meeting, an MS Teams meeting, in fact, exactly like the meeting we're having today. So we feel that somehow this is now part of our culture societally and worldwide, that this degree is as good and probably even better than an in-person degree, because it reflects what is going on out there constantly and is being changed and morphed as things evolve. So part of the charm of this degree is it reflects what we believe is a snapshot of what is the cutting edge in societal need and in industry today. In 2 or 3 years, we may be able to adapt the courses, depending upon what we see evolving, in industry and what society wants. So an upshot of this is it's a living cutting edge degree that is nimble enough to fit in working professional schedules.
Thank you so much. So I'd like to move on to a question for our panelists. So this is a Master of Advanced Study degree. It's a professional degree. And I'll start with Professor Mora. Could you tell us what you see as the value, what value does a professional degree bring to a student, to an engineer, as compared to perhaps an MS or a PhD? And then do you have any experience understanding how employers view professional degrees such as the Massey?
Sure, thanks, Joel. Yeah, so the academic degrees, MS, PhD, um, PhD in particular, are the focus is students are creating new knowledge. A professional degree like the Massey program is much more focused on application, and it's much more tied with industry. So there's really tight feedback loops between industry and our degree program. There are many companies, for example, that will uh, financially support their employees to pursue, online master's degrees like this one here. And that, I think, creates a tight feedback loop between companies and our program to figure out, how do we design the curriculum and the educational content so it really serves industry. Also what we're finding, even now with the first class that is coming in is the professional degrees are really, really good for folks who maybe want to pivot their career slightly, right? So for example, maybe they're in, tech, and then they want to pivot towards something related to, say, sustainability or climate. And it's really excellent for that because it's more directly related to how you can make impact, in the industry immediately. And to do it on your own time, right? Not just professional, but it being online and self-paced to an extent. It's excellent for those who already have lives where they're working, they have family, and exactly as Professor Zodi said, they can, take this content at a pace that works for the lives that they live.
Thank you. And Professor Wu, just wondering if you have anything to add to that. I know in particular, we'll talk a little bit about the classes that you've been developing, but um, especially because you've worked hard to find the balance between kind of the theory and the application in your coursework. If you have anything to add about the value of this professional degree.
Yeah, I think Professor Zodi and Mora have already, give a very good description of the benefit of this degree. I think this is a new experiment from our point of view as a faculty in this, at least in my field, that to develop this online program. But what I want to comment on is that me as the instructor of two courses that we're developing in this MSc program, we really put a lot of effort on tailor our course content toward what the industry, the current society wants to see from our students. So the course content will be very different from what a typical PhD graduate program would teach. And in that sense, in addition to that, you can learn on your own pace, on your own time. You also learn something different than what you would learn if you come to UC Berkeley campus and sit in our graduate course.
Yeah, Professor Mora, please.
Yeah, I just thought of a few more points that I wanted to share. So, a PhD and MS, I think you often will go quite deep into a specific field, right? But with these professional degrees, I think you get a good overview of multiple fields, which enables one to, maybe pivot their career or enter, into a particular field. And then, of course, I think for working professionals, for your job, you're going to, learn a lot about what's needed for the job on the job. Let me just give one example that I wanted to share with everybody. There's a student in my class this fall who has had an entire career in the tech industry doing software, working for various electronics companies. And then in the middle of the term, I guess, interviewed and got a position at Walmart working on their sustainability team. And he's taking my course, I'll explain more later, Engineering a Net Zero Carbon Future. And he was telling me that, during the interview process and in talking to people in his new job, he knew the jargon, he knew the lingo, he knew what questions to ask because of our course. And while he's still learning, it's now allowing him to pivot in this different position where he's making software tools to track their climate and sustainability. And so I was delighted to hear that story from him about just like literally before the class ended, he's putting, getting a new position and putting to practice what one is learning. So that's one story in one term before it's even over. And we'll probably have hundreds of stories like that.
Thank you for sharing that. And that's a great segue as well to our next question, which is the Massey curriculum was built to be specifically interdisciplinary rather than separated into what we see as traditional engineering disciplines, where if you might get an MS or a PhD, it might be in a particular discipline. So Professor Mueller, would you be able to tell us a little bit about why an interdisciplinary education is important for engineers today?
Yeah, I think engineering education is everyone we're speaking to here has gone through some engineering education, and it is naturally the problems we solve are very broad, and the disciplines evolved in certain directions to focus on certain things with courses that go together in certain directions. And I think of the mechanical engineering curriculum, for example, is extremely full, right? So there's a lot of courses in there, meaning there's also very little space for students doing a discipline degree to tailor it as they might prefer. And I think these interdisciplinary degrees allow students to sort of think about the problems that they're interested in or the societal needs perhaps that they identify, and to tailor their learning to give them the skills that they need for these, right? Because I think a lot of the problems we see nowadays, you can name whatever your favorite stressor is at the moment, are naturally interdisciplinary, right? So they require us to be able to bridge the gap between these narrow expertises that we have maybe as a background, but to other people. And I think that's where these interdisciplinary degrees really shine, in that they build engineers that can speak multiple languages, as it were, that are competent across disciplines, that of course have deep depth as well, but also like can span broader problems and broader techniques. So I think that's the real advantage there. And then beyond that, I think something that's maybe incidental, but also quite valuable, is the networks that you can build, the people that you can meet doing these are perhaps slightly broader than you would have otherwise, right? Because they come from different spaces. They come at this from another subdiscipline. And I think that can be very enriching, right? That can provide a lot of opportunities to grow that might not be as apparent if you do a typical siloed disciplinary education.
And Professor Zodi, on the same note of interdisciplinary education, and thinking about broader problems, just curious if you have anything else to add on there, and is there something special about Berkeley and Berkeley Engineering's mission to society that makes this interdisciplinary approach particularly impactful for engineers?
Yeah, I think that the outgrowth of these courses have been a reflection of, the extensive industrial work that our colleagues do. Our faculty are deeply involved in high tech in Silicon Valley and around the world. So the courses reflect that content. And that's one of the things that's important about Berkeley that really is a differentiator with other universities. The faculty are constantly refurbishing their classes as a reflection of what they see and what they work on in their research and what is demanded from them, from companies, from industry, from government. So when we designed these tracks, they were basically a reflection of what was a societal need. So electronics and systems engineering, advanced manufacturing and materials, infrastructure, energy and the environment, robotics and controls. Those things are cross-departmental. If we had the chance, in a fantasy world of the future, we would force our in-person classes and our in-person departments probably to be liquidated as well. The modern world or the modern, engineering college of the future wouldn't have those barriers of mechanical or civil or materials or electrical or bio. Those are things that were an outgrowth of the 20th century. But if we were to start today, we would probably do what we have in Mass E. Things would be grouped according to themes, not necessarily according to buildings and departments. So in this sense, the Mass E is actually superior to a normal degree because it allows students to take courses from all over the place according to what their needs are. So we're catering to the needs of the students and their interests and their careers and their futures, not necessarily trying to reflect on our internal balkanization. So when we designed these courses and this entire program, that was what was in mind. What would an individual person have the ability to take if they didn't have the barriers? And that's what you see as a reflection of how the Massey is constructed now.
And a follow-up question on that for anyone on the panel. You all are obviously PhDs yourselves, you're research faculty. How do you get that connection to industry? How do you all know, what does your interaction with industry look like? How do our prospective students know that you really have those connections? Anyone want to jump in?
Well, I think you can see it in the content of the courses themselves. I mean, they are in many cases a direct reflection of work that has been done by the faculty on high-end research, for example, with companies like Bosch or Apple or TSMC or Intel or, Bechtel. There's so many different companies that come to us because, of Berkeley's research prowess, that it's clearly reflected in the course content. That is not haphazard. These are things that were systematically developed as a reflection of work that had been done for the last 3 to 4 decades at UC Berkeley. And that's at least my experience.
Yeah, I also want to add that if any of you have come to Berkeley Engineering, you will be overwhelmed by how many talks coming by the our industry partners, industry leaders coming to our college and give a talks, meeting with our students, with our faculty, funding our research, etc. So we faculty in the College of Engineering, we get to know what the industry wants, not only through TV, newspaper, as what everybody else are doing, but we also have a first-hand experience of talking to them, making friends with them. Some of them, some of us, we even have our own company, startup company, and our students have company, and we advise them, and we send our students to be their employees, etc. So through those channels, we know what the problems industry want to solve, and we work together and develop solutions for them. And one good example is that at Berkeley College of Engineering, we have a center. It's called Better Center, Berkeley Emerging Technology Center. I'm part of that center. So that center, just next week, we're going to have a workshop. We will invite a lot of industry people, including the TSMC, Lam Research, Applied Materials, Intel, to come to join us, and we discuss the pressing problems that the industry face, especially in microelectronics. So through those interactions, we also feedback to the courses that we're teaching. And in this MSc course, we tailor the course content in a way that teach the students the fundamental knowledge that you learn and to be able to address the particular realistic problems that the industry is interested in.
I mean, one critical thing that I want to add to what Professor Wu indicated was that we are the #1 startup producer on the planet of all universities. Berkeley now has really come to the forefront, and it was a late starter. So in fact, that even makes it far more interesting, is that we were very startup resistant, let's say 15 years ago. But within the last 10 years in particular, there's been a huge increase in people having this entrepreneurial spirit. So that's also reflected in the courses, is it also equips people that if they decide that they want to go to the startup route, these skills really give them everything they would need to know. It's not a soft, fuzzy, wuzzy curriculum. This is not sort of a, master class in surveys. It really is very technical. So our key here is we're endowing people with the latest and greatest skills to make them successful as genuine engineers working on high-tech problems. So that's an important distinguishing feature here, because you often see in online courses the content might be watered down, or it might be, a mixture of, case studies or things of that sort. This thing is very, very tightly controlled in terms of reflecting what we believe is the latest and greatest from high-tech industry.
Yeah, Professor Mora, you want to add something?
I was just going to add in terms of the interaction with industry that here's what makes UC Berkeley unique and different is we're in Silicon Valley in the Bay Area. Basically, every single high-tech tech company in the world has at the very least an outpost in Silicon Valley, if not a research center. And folks there at those companies in these outposts, their job literally is to circle around the Bay Area, go to Berkeley, go to that other university down south, check out startups that are emerging out of these schools and try to absorb and learn and help the companies innovate and move forward. So, it's something I've seen being at other universities is that we're blessed because the campus is completely filled every single day, as Professor Wu was saying, with companies visiting, trying to interact, giving talks, and it creates this tight connection. And the reason we're also very tied is because the industry is filled with our students. We're decently large school. So, through our students, we all have students who are in industry who are feeding us back stories about here's what's going on, here's the skill sets that are relevant from what I learned, and here's the skill sets that are missing in the companies that we need to develop further. It's awesome. I mean, I feel very tight, and more than half of my research is funded by industry. I feel very tightly connected with industry and what they're thinking, yet at the same time, the freedom to think, creatively and intellectually about, okay, without the constraints of showing profit tomorrow, what sorts of innovations can we create to create the, industries of tomorrow?
Thank you. So I would love to get into some of the details about the courses. Professor Wu, Professor Mora, and Professor Muller have all developed really incredible courses, at least one each for the Mass E program. So just wondering if you could tell us, we'll start with Professor Mueller, if you could tell us a little bit about the course or courses you've developed, what students can kind of expect to get out of them, and how your course is really going to prepare students to solve those big engineering challenges.
Yeah, happy to. So I did the course, the number is 253. It's on autonomous flight, and the theme I picked up on, or what I wanted to teach students is how do we think about complex autonomous systems, and specifically highly dynamic systems. For example, flying autonomously. And we think here of things like drones, for example, delivery or something like this, or advanced aerial mobility. But the same topics apply to if you think about larger aircraft and the so-called simplified vehicle operations, or fully autonomous larger aircraft potentially down the road eventually. So the course is aimed at students that have some fundamental understanding of engineering, of course, but it aims to really endow them with a deep understanding of 3D mechanics and how things work in 3 dimensions. So this being, of course, one of the big challenges with flight is you're in this 3D space, and just how do you do that well? And then understanding how autonomy ties into this. So how do I make decisions? I make decisions now anthropomorphizing, but how does an autonomous system make decisions? How does it gather information about the environment? How do sensors, what data do I get from a sensor? How do I fuse sensor data to get some sort of unified view of what my system is doing? And then how do I respond to this? What actuator commands do I send to my vehicle, etc.? And how do I plan so that I get safe behavior, high performance, trajectory tracking, whatever it is I'm interested in doing. We also play a little bit with design trade-offs, so understanding, how when you create such a system, as with all engineering, everything is a trade-off. So what do you get and what do you lose as you sort of trade off different things? And then, the course has a project at the end which asks students to imagine a solution where you can use an autonomous aerial robot, and to think about what would the design look like? What kind of sensors do we need? How would I go about solving this problem? What is the autonomy stack, etc. And I think the real takeaway from this is, of course, specific knowledge to this domain of autonomous flight, but also just general understanding of autonomous systems. How do I go about creating an autonomous system? What is a control hierarchy? What are sensors? What is estimation? What is control? And how do these things tie together? And what do I mean when I say it should be safe, etc.? What do I mean by autonomy in general? So I think that's, I can go on for, I think, another 15 hours, but that would be the summary of the course.
Could I ask a follow-up question?
Of course.
What's the benefit? Is there what's gained or lost by learning a topic such as robotics online versus in person, having lab access, hardware access?
Yeah, so I think working with a physical system in front of you provides a lot of intuition, right? So just understanding the kinds of things that go wrong, like seeing a real sensor and being able to shake the thing and see how the output changes, feeling the temperature in the room change, and seeing the inertial measurement unit biases move around, something like this. This is intuition that I think you can only really get in person. But that being said, the core ideas, the analytic ideas, these translate very well in an online degree. And I think in an ideal world, we would all do everything. But the reality is, of course, we can't, for example, we can't develop passenger aircraft by building passenger aircraft. So the subtraction is necessary, and we are successful at the subtraction. And I think this is something that we exploit well in the online degree. So I think working with real systems is an advantage. And if you have the opportunity to do that, it's going to be in your benefit. But I think the online format does allow for a lot of the analytical understanding, even without that in-person lab experience.
Wonderful, thank you. And Professor Mora, could you tell us a little bit about the class you've been teaching this fall? And I believe you're working on another one right now as well.
Yes, absolutely. So the class that's already live at the moment is called Engineering a Net Zero Carbon Future. If you click on the links that are in the chat, it's Engine 210B. So Engineering a Net Zero Carbon Future, this is honestly a class that I've wanted to teach for years. And so finally, this was a nice opportunity to make a focused course on this topic. And I think this is a course where if you want that introduction and overview to the key issues related to moving activity on Earth, human activity on Earth and our economies towards a net zero future, what are the different technologies? So we talk about electricity generation, renewable energy, nuclear, fossil fuels. We talk about energy storage. We talk about electrified transportation. We even talk about carbon capture technologies, carbon sequestration. We talk a little bit about policy and market mechanisms, economics to help facilitate this net zero carbon future. Very exciting topic. I find that it's a topic that lends itself to a lot of really interesting conversations. So there's a lot of interactive discussion that students, although it's online and asynchronous, there's moments in the course where students will do interactive conversations via these discussion boards, and those are very interesting. The second course that should go live for spring 2025, so just after the new year, is called Optimization of Engineering Systems. The course number is Engine 238C. And so this is a much more technical course. And, it's really all about optimization. Optimization, every field, I think, can find ways to use optimization it's such a mathematical way to do engineering where you're trying to design something to achieve some sort of objective under some sort of constraints. And so I love the topic because it makes very concise and clear and mathematical and clean, an engineering task in terms of this mathematical optimization. And so we talk about all the most relevant modern tools in optimization, convex optimization. And although the title of the course doesn't reflect this, a whole unit of it is about optimization for machine learning. So if you're really excited about machine learning and you want to understand the mathematics behind it, that's actually where the course culminates, is basically optimization for machine learning. So very excited for students to start taking that in spring. There'll probably be other courses that I hope to develop if I find the time, and in future webinars, I'll introduce those.
Thank you. Professor Wu.
Okay, so just like Professor Mora, I currently have one course live this semester, which is a semiconductor course. I am also working on a second course, which is a quantum physics for engineers that hopefully will go on live next semester. So let me talk about my first course, semiconductors. As Professor Mora just mentioned machine learning and AI, and everybody, especially, the Nobel Prize in physics and chemistry this year went to people who use AI to advance traditional science. So AI and machine learning will be getting more and more important in industry in all the different fields. But AI is powered by chips, and chips are made of semiconductors. So without semiconductors, you really cannot really do anything that you can imagine with the microelectronics industry. So what are semiconductors? Why semiconductors are important? And we all learn physics and chemistry in undergrad. We know atoms, carbon atoms, silicon atoms, right? But how do you go from single atoms to semiconductors? You put different atoms together, they don't have necessarily form a semiconductor. So what is a semiconductor? Why semiconductor is necessary, needed to make a transistor and make a chip? And that is the kind of question that I want our student to be able to answer. So in this particular course is based on a semiconductor course that I've been teaching in my department for the regular in-person course in the past 15 years. But I condensed that semiconductor course into a one-unit online course. I obviously get rid of a lot of technical details, but I also added new things. So for example, current microelectronics industry, when they make chips with higher and higher density and higher and higher, power requirement, they have to worry about the heat dissipation. How do you get the heat out from the chip? Otherwise, your chip will heat up and you will slow down the performance and lower the lifetime. So this relates to the thermal conductivity of semiconductors, which is a relatively, I would say, a new research field, because semiconductors operate based on their electronic property, not really on a thermal property. But I do research in that field of looking into the thermal conductivity of semiconductors. So I know the literature very well. So I included a little bit of that ingredient in the course I'm developing. So through this semiconductor course, MSE course that I'm offering, I hope you can build the connection from what you learned in undergrad or even high school atoms, basic chemistry, all the way to the materials, silicon, gallium arsenide, nitride semiconductors that people are using to make computer chips, to make solar cells, to make light emitting diodes. So that's the first course I'm developing, which is currently online. The second course is called Quantum Physics for Engineers. And this is because I observed that although currently quantum science and technology are mostly done in research labs, but we would anticipate, in the future industry, they are going to have a large importance of quantum science. So, for example, for communication, quantum computing, quantum sensing, they could do better or much better than the traditional classical computers. So in that sense, I want to prepare our engineers with a solid foundation in understanding quantum physics. And this is a course that I learned when I was a graduate student from a physics department. But the physicists, they teach it in a way that teach the student how to really do research on quantum science, not really tailored toward potential application in the industry. So in this course, I teach first the basic quantum mechanics for our students, and then I will make a connection of that to what is currently very active in research about quantum communication, quantum sensing, etc. So that after you learn this course, you will be in a very good position to at least talk to your colleagues about future quantum technology that will hopefully come into our industry in a not too long future. In this way, I think my quantum physics for engineer course would also be a very good like foundational course for people who are curious about quantum physics, right? Who are interested in looking at the problem they have in their own hand using the different quantum mechanical perspective, so that maybe there is something new that you can develop in your own position if you are an industry engineer. So that's my two courses that I can introduce.
Thank you. I'm curious, in addition to you all have expounded upon specific areas of knowledge, are there other characteristics or experiences that make somebody really competitive in today's industry workforce? How important is a master's degree period versus having maybe a bachelor's degree in engineering? Anything else you might be able to say about how to be really competitive in the workforce today?
Unfortunately, for most real engineering problems, a bachelor's degree is no longer enough. It's just like the evolution from, 200 years ago, an elementary school education was good enough. Then a high school education was good enough. Then a bachelor's degree was good enough. And I think we've now transitioned. There's a huge amount of knowledge in engineering that has to be absorbed, people to master a certain topic or a certain genre of topics. So, regardless of whether it's Mass E or another degree, a master's degree is almost essential now for a practicing engineer. Of course, there's some exceptions, but generally speaking, it does equip a modern engineer with the essential tools because there are many more things to learn. 20 years ago, there was very little computer programming. There was no machine learning. There were no, computational optics. There was no telecommunications. All of these things have evolved to become a normal, tool for any modern engineer in any field, whether it's civil or mechanical or materials or electrical. They need to know these things. So the Mass E really endows in a very lean and targeted way exactly the information people need for their planned future. So we try to make it also flexible enough that it reflects also their interests. In many programs or degrees that you find, the flexibility really isn't there. There's a certain set of courses, you have to take them, then you barely have enough to do a couple of electives, and then you graduate and you go off on your happy way. Now this is different. We designed this in such a way for maximum rigor and maximum flexibility at the same time. That is not an easy thing to do, and it took years to figure out what we believe is the secret sauce to this kind of an approach. Most modern curricula now in top schools are still trapped or handicapped in a way by that they have the legacy of the past constraining them. They have constraints due to official documentation or university rules that, force a curriculum to behave a certain way. What we were able to do and to work with the UC system is to convince them that this is the modern way in which people need to learn. And we've had wholehearted support. And in fact, there are many other degrees now that are trying to emulate this kind of model. So we feel it's a reflection of a modern way to get, information across that isn't easy, but is rigorous and does reflect what society and industry really needs. So the Mass E is different than other older degrees, but it's a good kind of different.
Yeah, Professor
Yeah.
Mara.
Yeah, can I add? I think Professor Zodi is absolutely spot on, and I want to add just another perspective. So on the question of how is the Massey preparing its students to be competitive in the workforce, I actually think that's not enough. It's not enough. It's not enough for our goal to just produce competitive potential employees, right? Let me back up into the point I really want to make. So just in California, for example, we have the California State University system, huge, biggest university in the world when you aggregate all the campuses, does an amazing job for producing competitive people that go into the workforce. Excellent at that. So why do we need UC Berkeley? Why do we need Massey? I think it's not enough because we want our students to really create and innovate and be the leaders for the future industry, not just fill the industry as it's existed for the past 50 years. So to do that, they need a deep fundamental understanding, of the technologies and the concepts. They need to understand the step function up in technologies and opportunities and challenges that we face. And they need to understand how to put these together to innovate and create and be the leaders that we need to guide society, industry, for the future. And I don't think every university needs to do that. We need places that can just make a competitive workforce. But I think we hold, and I don't mean this necessarily in an arrogant way. I think it's just how we're structured and the challenge that we have to take on. And so I think for students who are excited about that, right? They don't just want to take a competitive position in the workforce. They want to create new industries and be thought leaders. And as part of that, have that strong technical foundation to be able to lead that. I think that's why you come. And if it's just being competitive, then I think there's a lot of excellent programs.
I think that's also one of the things about UC Berkeley that speaks to people. Students who come to Berkeley and faculty who come to Berkeley and staff even want to make a difference in the world. They want to serve the public, serve the state of California. And I'm glad to hear you say that it's about more than just making people competitive. It's really about being able to make a difference. Okay. I'm happy to let any of our panelists say anything else in closing, anything you wanted to add, or we're also happy to take any questions from the audience.
Maybe just a comment here in terms of being competitive. I think we as faculty think a lot about what's good for students, how do we make the strongest engineers. But I think what I've seen from the students in the Massey program at the moment is also just that there's this bottom-up desire from students who see a need, and they see how the Massey program helps them do something that I am not aware of, right? So they're working on some problem and they notice that they need some additional knowledge or they're lacking something. And this is a way for them to sort of, tailor make their own curriculum, their own interdisciplinary set of courses, etc., to achieve that goal, which I might not be aware of, right? And this flexibility that this program has allows for these students to become hyper competitive in this niche that they identify, right? That they are aware of just because of where they are and the things that they are doing in their careers, etc. And I think that's maybe one thing that I think is very unique about the Mass E compared to, say, a traditional program we have.
Can I add one more point? I really want to hear what the attendees want to ask about, but I just want to say that I now understand that what we're producing in the Mass E program is really a premium experience. I didn't realize this coming into it, but you know, there are a lot of online programs, they just put video camera in the back of the classroom and they toss that online, and that's your experience. You know, this is highly produced, built from the ground up to be online, where it's very interactive, short videos, little questions, you know, within the videos, and a lot of interactive activity. So it is truly from the ground up an online learning experience. It's not just camera in the back of a room and toss it online. So you might not understand it until you're actually in it, and then you start to realize this is a different level.
Yeah, I think during the pandemic, right, a lot of educators pivoted to remote education, and that is not the same as online education. And that's something we've been learning a lot of as we're building these courses for the Mass E. And I think it really does create a wonderful experience for students. Yeah, Professor Wu.
Yeah, so I want to echo with what Professor Moran said. You know, I work with Coursera for these two courses, and I have to say that I'm very impressed. They are very professional. You know, the very careful about every single details of the coursework. So this is um, about the videos, the homework, the assignment, etc. I think we spend a lot of time on that. Is definitely worth you to just go in and take a look on the videos on the curriculum. I also want to say that making this course together with Coursera is an educational journey for myself. I used to teach a big class in a classroom and interact with a student for 1 hour and a half, and then that's it. But this development of this Mass E course forced me to think about my teaching style differently. And this modular way of teaching the course is a eye-opening experience for myself as an instructor. I have to think about there is a complicated concept. I have to divide that concept into multiple aspects and then teach them in a very coherent way, but in a very condensed, concise way within 7-8 minutes, and then stop over there and wait for the student to digest and then move on to the next topic. And I think this is a very good way to learn especially engineering topics. I would imagine this is not a good way to learn humanity or social science topics, but this is really a very efficient and inspiring way to learn specific engineering topics like what I'm teaching in my courses.
Okay, we do have a question from an audience member. Question is, are there any industry development reports from state government or organizations representing the market demand that is related to the program?
So you mean reports that are saying we should have online degree programs?
Let's see.
What is the question's nature? I'm a little puzzled.
So this is from Jeffrey. Are you able to unmute yourself and maybe clarify your question? Can they unmute? Tong, do you know if they can unmute themselves, or does it have to be entered?
You can just repeat the question again.
Okay. Are there any industry development reports from state government or organizations representing the market demand that is related to the program?
Yes, I mean, almost all the major universities and state entities are asking that, public institutions like the University of California system pivot to an online degree portfolio, because simply the demand for people to get an education in California, for example, is extraordinarily overcrowded. So there are finite amounts of space on any physical domain like the University of California. If you ever visit UC Berkeley, it's every square millimeter is packed. And so there's going to be very difficult times in the future for us to even have our normal classes have the ability for people to sit, in seats. So online now is more or less, lingua franca even for our normal classes, simply because, the modern world is a world where people are halfway across a city and can't make it back to class. They can at least watch online, or they can come in person, or they can do both. So the Mass E is a reflection of also the demands that have been put on us by the state, by federal governments, that we need to have more students, in the United States and across the planet educated, but we want to give access to them. And there's either we build universities that are gigantic, which we can't because, most places are landlocked or constrained. Therefore, the mandate is, of course, to move in an online direction. Certain if you Google demand for online degrees and Google the keywords that you asked in your question, you should be able to find many reports or documentation on what those state and federal agencies want.
Oh, we have an update to the question that was asked. Jeffrey says, I mean the market demand related to the 4 concentrations provided by the program.
Yeah, the 4 concentrations were in strong collaboration with industry and companies, that are our partners as to who they're looking for as future employees. So those, without revealing exactly what each company specifically said, those 4 areas went through a very rigorous multi-round type of vetting. We first started with 12 topics. And the 12 topics were then vetted with a variety of different companies, and companies that we deal with, NGOs, industry partners throughout the United States and in the Bay Area. And those were the 4 that they indicated were really what they're looking for.
Thank you. And Alejandro, I think we do actually have a chance to unmute. So we're going to let you turn on your mic if you'd like to ask your question directly. Alejandro, can you hear us? I saw you just unmute for a second there. Probably need to hit that unmute button one more time. Okay, while we get Alejandro sorted, let's see. The question, we have a new question in the chat. So it is, I'm an airline pilot and former flight instructor with background in industrial engineering, interested in flying robots as I'm flying a lot over remote areas. I can see a lot of opportunities which only can do with drones. What's your opinion about that type of background to continue in this field?
Yeah, I suppose this is directed at me. I think, this sounds like the kind of student I would love to have in the class, right? So someone who brings a deep domain knowledge in flight, perhaps not so much structural mechanics or something as a mechanical engineer might have. But I think, if you come from an industrial engineering background, you have knowledge of the mathematics that is required to succeed in this course. You have this domain expertise related to flight. And then I think you also will just bring a deep insight into potential use cases and problem areas and so on. So I think, this is a student that would, I think, succeed and do well in the course, but it's also a student I would love to have in the course, and I look forward to interacting with during office hours and to see the project that they work on.
Okay, thank you. We managed to fill up all of our hour here. So I just want to thank all of our panelists for joining us today, as well as all of our listeners in the audience. Thanks for joining this really interesting discussion. Hope you learned a lot about the Massey and how this type of program can really help you achieve things in your career. And I'm just going to show one really quick slide here with our contact information if you'd like to get in touch with an enrollment counselor, learn more about the Mass E program, and keep an eye on our future application deadlines. So thank you very much for everybody's time and effort today, and we look forward to seeing you at the next event.
Take care. Bye.
Thank you. Bye.